Welcome students. Now the next part of this topic metal cutting we are going to see is the machining. So in the machining we are going to see first the machining time calculation part. Okay, for the various cutting operations like for plane turning, face turning, milling, drilling, for grinding, etc. So we are going to start with now the machining, and here the very important thing that we are going to see, the machining time calculation. Machining time calculation. So let us take the first operation, that is a turning operation or plane turning operation we take. So say here is the cylindrical bar is given for us for this turning operation. Okay, tool is having the position at here. Okay, so of course this is the approach for the tool, and if the tool is having some over travel after completion the machining, so this is the over travel OT. Okay, and the diameter of this bar, that is original diameter, is D, and say after the machining or after having this first cut, so it is going to reduce to the diameter say D. If it is not given, then for the speed calculation, for the speed calculation of this job, okay, you can use the uncut diameter for the speed calculation, because you know that the cutting velocity is what? Pi dn divided by 1000, which is in meter per minute. But when you calculate n, it is equal to thousands times Vc divided by pi d. So here d, you rather take this, the uncut diameter. D should be the uncut diameter, that is original diameter. Or if the next diameter is given, so after the first cut, so you can have this diameter as the D original plus say D after cut divided by 2. You can take the average value also. Okay, but generally you can take this uncut diameter for the speed calculation. Okay, now we are interested to find out what is the total length traveled by the tool. Say it is equal to capital L. So if I want this total travel length of the tool, so it will be equal to what? This length of the machine part in that plus approach if given plus over travel, isn't it? So these are the optional things. See, if it is given, then only take, otherwise you can direct have this small l as a capital L. Okay, once you get this length, you have this RPM of the spindle, okay, with which the job is rotating, and if you have this feed given to this tool, okay, we are very much clear now. F1 is our feed per tooth, F2 is our feed in mm per revolution, and F3 is our table feed, which is simply in mm per minute. So instead of this F2, you can directly use the F3 also if the direct value of F3 is given instead of giving the n in the question. You know that what is F3? It is F2 into n. So what is the formula for the time calculation? So how to calculate the machining time? So I am talking for the single cut, what is time? So the time for a single cut, I can write this length of the tool travel, that is total length of the tool travel, divided by this table feed, which is in, say this is in mm. Table feed, you know that it is in mm per minute. So ultimately what you will get? The unit for the time is minute. Or you know that the F3 is what? F3 is given by F2 into n. This T is also is equal to L divided by F2 into n. So this is what? mm divided by mm per revolution into revolution per minute. So you will get here minute again. Okay, so this is the time per cut. Okay, time per cut. And if you have the number of cuts, then multiply by the number of cuts, you will get the total time. The total time. That is time per cut, which is L divided by F2 into N into the number of cuts. So in this way, you can able to get the machining time. Okay, so this is the first thing. Now here, so the second condition, if I want to take, that is if I want to have the face turning operation, I want to have face turning here, then what? The tool will be here now. So in this position, tool is here, and this is the feed direction, isn't it? And this is, say, depth of cut is nothing but the T1, and width of chip is equal to is equal to width of cut, that we know, we have seen in this oblique to orthogonal cutting of analysis. So here the tool, the movement of the tool will be up to what? Say if D is the diameter of this cylindrical bar, then D by 2 is the tool movement, isn't it? So only the thing is that the time per cut you can have is how much? L divided by, again, this F2 N to N. Okay, but length of the tool travel is how much again now? For the facing operation, up to the center tool will go, because it will take the radial cut, isn't it? So length will be what? This D by 2. Length will be what? This D by 2. And if you have want the approach, and actually approach only, over travel no need, directly up to center we can have this entire face. This is the face, you can go with the tool. Okay, so tool is here, so go up to this, the entire face is going to have the facing operation, isn't it? So if you have, you can add the approach if given, otherwise length is D by 2 divided by feed into the N. You will get the time in, again, in minutes. So this is for the second case you can have for the face turning operation. Face turning operation. Okay. Now say third case on this lathe machine, I am having again the taper turning operation. Taper turning operation. So you can have the various methods. You can have the compound rest method, isn't it? You are having special attachment for the turning, taper turning. You can have the form taper turning tool, isn't it? So then set over method. So these are the 3-4 methods are available for producing the taper on the given workpiece on the lathe machine, isn't it? So let us, here we are going to find the time which is required for taper turning. So let us see how much it is. The third operation on the lathe, we are going for the taper turning operation. Okay, compound slide. Then we are having the offset method or set over method. We are having form tool. Okay, for producing the taper on the given workpiece on the lathe machine. So here we are going to find the time. Say, let us see that we are having this workpiece, cylindrical workpiece, of course, and now this is the tool. Okay, we are having here, and this is the depth of cut is taken for the, of course, taper turning operation. Number of cuts we are required. It is not possible to have the operation, the entire operation in single cut. So of course, step by step we have to go. So say if this is the depth of cut is a D1 max, and please remember, for every cut we are having the same depth of cut. So we are getting here the first, for the first cut we are getting this value. This is nothing but, say, theta, isn't it? Okay, so this is the value of taper angle theta. So here, say for the first cut, so the length of the cut is this, say L1 is the length of cut, and angle which is taper angle produced is say theta, and what is the depth of cut is given as d1 max, or we have chosen this d1 max as a depth of cut. So again here tell me, like that we are going on the number of cuts to get the required taper on the component. Say this is length L1, then next cut it is L2, next cut it is L3, like that. And every time the angle is, taper angle is going to be same. Say it is theta and it is say theta. Okay. Now here we know that how to calculate machining time is equal to L divided by F2 into N. So F2 and N is of course there, the spindle rotation will be there, and the feed given to the tool is there. Now this is the question of this length. So how much length you are going to machine in every cut in this taper turning? Let us see. So if I write here, say sine theta for the first cut I am writing. So what is that? So this is here is nothing but, this is nothing but, see, sine theta is this d1 max divided by this hypotenuse is L1. So this is d1 max divided by L1. So what is the length you got cut in the first cut? That is L1 is equal to d1 max divided by sine theta. So what is 1 upon sine theta? So it is nothing but the cosec theta. So this is the length of cut you got in the first cut. Okay, like that if you go for the second cut, as I told you, depth of cut will be same again. This is d1 max. So in totality 2 d1 max is the depth of cut you get. And here for the second cut, what is length get machined? That is, I will write again, sine theta is equal to, now how much depth? That is 2d max, 2d1 max, isn't it? Divided by length will be L2. So L2 will be of 2d1 max into cosec theta. Like that you go for the third cut, you will get the third length, that is, now the depth of cut becomes C, again this d1 max, then in totality 3 d1 max. So 3 d1 max, isn't it? So like that you will get the lengths, and of course the operation is going to have the number of cuts. So I can write like this. So this total time, if I want to write, it will be say L1 divided by F2 into N plus L2 divided by F2 into N plus L3 divided by F2 into N. That, like that, how many number of cuts that we have taken. So in this way I can make a common out of this, that is 1 upon F2 into N, and for L1 plus L2 plus L3 and so on, what I can write? 1 upon F2 into N. L1 is what? D1 max cosec theta plus 2 D1 max cosec theta, like that, plus so on. Okay, so out of this bracket also I can make a common what? Common thing is what? D1 max cosec theta divided by F2 into N into bracket 1 plus 2 plus 3 plus so on, isn't it? So what is this? Nothing but what? This is natural number series, isn't it? No. D1 max cosec theta divided by F2 into N into bracket what? N into bracket N plus 1 divided by 2, isn't it? So this is nothing but what? The total time required for this taper turning operation, where N is what? The number of cuts. N is what? The number of cuts. Okay, so this is how. And D1 max is what? This is the depth of cut for every cut, of course. F2 is the speed in mm per revolution, and N is the RPM of the spindle or the job. So in this way we can able to calculate the machining time for taper turning operation on the lathe machine. Okay, thank you.